Okay, so I'll start today's class. So this is the week 3 for reinforcement learning and NPTEL self-trust. Okay, so first I want to begin by saying that last class I showed you a code. I think many of you might have misunderstood what I was trying to plot there. So as you know, there are uh, so we have uh, cumulative rewards, and also we have cumulative regret. All this I'm specifying under multi-mandate setting. So in the last time, while I showed the code, uh, I plotted cumulative regret. So uh, whenever you're trying to find out an algorithm, you're trying to minimize the regret but maximize the reward. Do you see that both are the same? Is the same thing you're trying to do? The same mathematical formulation is the same. Either you're trying to maximize the reward or you're trying to minimize the regret. So what happens is, so suppose you have maximize rewards, and this is maximize, and another thing is you can minimize. Sorry. You can minimize true reward or optimal reward minus calculated reward, or the policy that you choose, the reward that the policy that you choose gives the reward, that reward. So subtraction, so you're trying to either maximizing this interior term or you're trying to minimizing the whole term. So in the last class what I showed you was I was minimizing the regret. So this whole term is called the regret. So I guess that might have confused some of you in the last class, but yeah, you could either maximize rewards or you could either minimize regret. You could do one of them. So now in this tutorial, at this end session, I'll go through another code which I've made more better than the last time, so that you understand what is going on in the MAB with different distributions and with different settings, where you try to estimate the expected reward for each and every arm. And I'll leave a small assignment so that you can try out different algorithms on your own. So you just no need to yeah. So I'll post it while posting it on YouTube this time. In the description I'll give a Google Colab link for the new code that I have shown on MAB. So that will have many open spaces. So in that open spaces, what you need to do is you need to fill your own code for different algorithms like epsilon greedy, UCB, Thompson sampling, median elimination, pack. Whatever you can try it out all those algorithms, and you can see that okay, what happens in changing the parameters, like if I run it for a long time, what happens, if I run it for a short time, what happens in those conditions, but we'll see it later. So for first this week's these things, I'll just go through all the things that sir has iterated in week 3. Do you guys have any doubt other than this, or do you want me to continue with my class? Okay, maybe I'll continue with my class. So first you have policy. So yeah, so policy phi t a. So it's defined as probability that you will choose action A at time t. So this is what a policy is. I hope this is clear to everyone. Okay, and then something sir told something of policy search. Right. So in policy search, sir try to parameterize the policy with respect to theta. But before going to that, we'll uh, we'll just do one example. I think the same example as sir done also in the class. So I'll just do one of the examples. So suppose you have binary bandit. With rewards belongs to 0 and 1. And there are two arms. So now two arms has each have different distribution. So two arms each have different distribution. So if you pick arm 1, the probability of getting 1 is different, and if you pick arm 2, the probability of getting the probability of getting 1 less reward is different for arm 2. So if you have this kind of setting, so what you do is you have a policy. It says that okay, I'll pick arm 1 with this probability, I'll pick arm 2 with some other probability. So that is your pi t of 1 and pi t of 2. So let me name the arms 1 and 2. Okay, so now suppose I pick arm 80, sum of any one of them. Suppose I pick arm 1, suppose 80 is equal to 1. So I pick arm 1, maybe 1 become confusing. So let's say this as A and B. Okay, so suppose I pick arm A at time instant t and I get a reward pi t. So I have a policy at pi t minus 1. It says that with what probability I'll pick a t minus 1 is equal to a, and with at pi t minus 1 I have a b which says with what probability I'll pick b. Because at each time instant you need to pick any one of the arm. I think it's very clear that you can say the probability of a t minus 1 equal to b is equal to 1 minus probability of a t minus 1 equal to a. So either you pick arm a or you pick arm b, since you have two arms. So if RT is equal to 1, then you have pi t plus 1. So you need to update the probability of picking the arm A. So AT is equal to A is equal to, so you had a, so pi t is equal to A, pi t is equal to A plus alpha into 1 minus pi t into pi t of A. And so pi t plus 1 of B is equal to pi t of B into 1 minus alpha. I hope it's clear that how this term has, this update rule has come. Do you guys have any doubt in this update rule? If you have a doubt, you could ask me. Okay, so I hope it's clear to everyone. Okay, so it means that what is the intuition behind this is, if you pick an arm A at time t and you get a good reward, so that means you are thinking that okay, maybe AT has a higher probability of getting me a reward 1, so you are updating the probability of picking A again. So you're increasing the probability of picking A at the next instance. So what this term does is, it increases the probability by the previous term. So suppose previously you had 0.3 probability of picking A. Now since you picked A and you got a good reward, you are trying to increase the probability of picking the arm which gives you a higher reward. So yeah, so this is one of the thing. And you could similarly do the opposite, like if RT is equal to 0, then you decrease the probability of the arm that you have picked, and automatically the next one goes by normalization, because you have the condition that pi t plus 1a plus pi t plus 1b is equal to 1. This needs to be satisfied since pi is a distribution over the two arms a and b. Okay, so I hope that is also clear right now. So sir gave many these things on these types of things on what alpha should be and what alpha should not be. So I hope that is also clear. Okay, so next I think sir we're going to policy grading methods. So policy grading. Here sir did a bunch of software service like linear reward, penalty, algorithm, and there were some things. Yeah, so I gave multiple things depending on what alpha and beta should be. But if you have got a positive reward algo, and if you have a negative, if you have when RT is equal to 0, then you with what rate you should decrease the probability, with what rate should penalize for getting a bad reward, and with what rate you should increase the probability of picking the action if you get a good reward. Depending on those two parameters, alpha and beta, sir gave I think three different notions of algorithms. So next is policy grading. So what you do is, since pi's are distributions, then parameterize your distributions using some parameters. So suppose you have a Gaussian, so you can parameterize your Gaussian using the mean and the variance. So if you know the mean and variance of Gaussian, you can write down the whole Gaussian distribution equation, and you can just find the probability of x being less than or greater than or something. So distribution, it's not just distribution. You can most of the times you can parameterize functions. So what you try to do is, since you don't know what the underlying distribution is, so you assume that the underlying distribution is something, and then you try to parameterize that underlying distribution, and now you don't know the parameter theta. So now you are trying to update the parameter theta each and every time, so that you reach to the true distribution. So what I'm trying to say is, suppose you have Gaussian with the mu and sigma. You don't know what the mu is, what the sigma is. In this problem, actually, you want to find out the mu of this thing. So now you have an arm. Let's call it A. You have an arm here, which has a underlying Gaussian distribution from which rewards are sampled with mean mu prime and sigma prime. You don't know mu prime and sigma prime. You want to know mu prime and sigma prime. So what you do is, you say that okay, so mu and sigma are unknown. You want to try to go it towards mu prime and sigma prime. Okay, so now this is all a different thing. Now in policy grading, what you do is, since you have pi t of A, which is actually a probability of you picking the arm, probability at 8 is equal to. So it's probability. So now you have a probability distribution. Now this probability distribution could be anything. If you had discrete arms, so it will not be Gaussian, so it will be with some distribution. So you'll have some PMF associated with all the arms. So now you don't know what with what distribution I need to pick it. So you assume that it's maybe binomial, or it's multinomial, or it's some type of distribution, and then you parameterize it, and then you start to know the parameters, so that you get to the optimal policy. Okay, so now what happens is, so suppose you know a policy, you want to know how good that policy is. So that is defined by a function called expected payoff. Expected payoff. So what expected payoff does is, so suppose you have a policy pi. Okay, the function which takes the policy and gives out a real number. So this real number tells you that how good your policy is. So you either want to maximize this expected payoff, or you want to minimize your expected regret. It could be anything. Like depending on the problem setting, you could have both ways. Like you could try to maximize the expected payoff, or you could try to minimize the expected regret. But given a policy, you'll always have an expected payoff, and given a policy, you'll always have an expected regret. So you want to try to find that policy which will maximize your expected. So it's like you have many number of policies. So among all these policies, you are trying to find the policy which gives you the maximum payoff. So this function is basically denoted by expectation of RT. And yeah, I think sir gave you the whole derivation for this. I am sure you guys don't have any doubts in that. You guys have any doubts? So guys, no doubts. So yeah, so what you get from this is you get a way of how to update theta. So if theta was your parameter to update, so what I'm going to do is I'm going to parameterize my policy with respect to theta. this policy distribution, I can parameterize it theta. So now I'm trying to find the theta which gives me a good expected payoff. So maximum expected payoff. Since I'm trying to find the maximum expected payoff, it is it's a ascent. So you're trying to move in the direction where you are maximizing some function. So what you do is you update theta at each and every step. Theta plus some alpha into gradient of theta phi. Now since phi is dependent on theta, I can write. So this is my update policy. This is my update. This is how I update the parameters so that I can update my policies. But that is also clear. Then sir mentioned, I think, reinforce. So yeah, so in the reinforce, I think the update. So actually what this boils down to is theta t plus 1 is equal to theta t plus alpha grad theta by theta. And sir did some manipulations here. I think he divided it by yeah. So okay. So this was the batch setting. There was a batch setting and incremental setting. I'm going to. If you have any doubts, you could ask me. So then before the reinforcement, there was an incremental version of it. So there was an incremental version of it. So in the incremental version, what you had was get theta t is equal to alpha t into r t into grad phi a t by phi a t. And this is what this was. So yeah. Now this could be written as theta t is equal to alpha t r t, where grad theta t, how do you get grad theta t is, so you have theta t plus 1 is equal to theta t plus grad theta t. So grad theta t is effectively theta t plus 1 minus theta t. So now if you put here theta t plus 1 minus theta t, you bring the theta t over this side. So you have theta t plus 1 is equal to theta t plus the gradient term. So this you could write as log phi at theta phi. Yeah. Does anyone connect?
Hi Aniket, sorry, I wanted to let you finish first, but anyway, after you're done, can you show the how to solve question 3 of the non-graded assignment after this, because that's also related to the reinforce algorithm.
Okay, the Gaussian one, right?
Yes.
The Gaussian. Yeah. I'll show that.
Thank you.
I think I'll do it right now. I'll just do it right now. So do. Okay, so this is do with respect to theta, right? So I hope there is no confusion in this step. How we are getting this from this? So if you partially differentiate this function with respect to theta t, if you use chain rule, what we get is 1 by phi a t theta t, and then they add this respect to theta phi a t. So it's basically like this. But then this is a much more simpler way to work. And so if you use this, is the reinforce version. Okay, so do you want me to go through directly go to the Gaussian one, or do you want me to once do what sir has done in class, but do action and arbitrary, do action, some rewards, arbitrary rewards or something. So maybe I'll directly go into the Gaussian. So what you have is phi a sigma is equal to 1 by root 2 pi sigma e power minus a minus b whole square by 2 sigma square. This is your pi. So now I'll just write down the steps which will make it easier for you to find out. So find log of mu sigma. What you get is log. So whenever log you use exponential, the log with base yeah. So 1 by root pi minus a minus mu square by mu sigma square. Okay. So this I can write as log 1 by root 2 pi minus sigma. Log sigma plus a minus mu whole square by mu sigma square. So since I told you before that I have two parameters here, mu and sigma. So I need to update, since this thing, I need to update both my parameters. So mu is also parameter, sigma is also parameter. So I need to find a definition for updating mu. I need to find a parameter equation for updating sigma. So when I am trying to update mu, I will take the differentiation with respect to mu, and I am partial differentiation. So it's here in the reinforcement. Yeah, partial differentiation I'll do with respect to mu. When it is sigma, I'll do the partial differentiation with respect to sigma. So first I'm trying calculating, but I'm doing the update equation for mu. That is what we want. We want to update mu. So first I'll do the partial differentiation with respect to mu. So partial, this goes to 0, this goes to 0, and you have minus of minus 2 a minus mu by 2 sigma square due to the cancel a minus mu by sigma square. Okay. So would you help out with the update equation? So if I have mu p plus 1 would be equal to mu p plus
alpha into 1 minus mu t.
Alpha into
1 minus.
Why 1 minus? What does the reinforcement algorithm tell you?
I thought it was the. Okay, this one. Okay.
And I just calculated this. I hope it's clear. I just calculated this.
Right. Yeah. That I got.
Not this. Sorry. This.
The delta, the below one.
Yeah.
Yes.
Yeah. So this is basically. Sorry. So this is basically theta t plus 1 minus theta t is equal to this whole term. Alpha, I'm taking it to be alpha for all time.
Right.
Into this. Yeah. So I'll get RT into a minus mu by sigma square. And that is the answer. One of okay. I don't have the answers. Yeah, that should be one. And then I can find the. Should I find the update equation for sigma, or are you guys comfortable finding the update equation for sigma?
Well, I think doing sigma is. I think I can manage it now that I know what to do. I was going wrong in this place. I was doing 1 minus mu t. So
Okay,
that was the problem.
Yeah, so that derivation I didn't derive here. Like how we got from that 1 minus. Where is it? Yeah, from this to this. I think it's in Sir notes. Sir's this thing, you can check it out. If you still have doubt in that, it's okay. But incremental version, that's not the batch version. The incremental version, your final equation should be this thing. Hello.
Yeah. Thanks, Aniket.
Okay, so since we are done with the Gaussian one, okay. Next, you guys have any doubts in contextual bandits? I think Sir has not touched much in contextual bandits. It's just that in contextual bandits, it's similar to it's similar to an MDP problem where you have like different settings of, like here the environment is constant at all time. So you have the same bandit problem at each and every time, but there what happens is at each and every time you could be picking out for different bandit problems. So what would happen is you have maybe binary problem 1 might have binary problem 2, might be binary problem 3. Now each of this has arm A, arm B, arm C, arm A, arm B, arm C, arm A, arm B, arm C. These guys each time have different reward distributions. This has different reward distributions. This has different reward distributions. So suppose at time first instance, suppose this is what is given to you. The next instance you get 3, and the next instance you get 2. That is also random. So at each time instance when you're picking up, so suppose A has a good reward in this, A might have a bad reward in these two. B might have very bad reward here, but might have good when you're playing NLP. So this whole setup is what is the contextual bandwidths. So yeah, I think you can pose it as a interview problem, but I think that's one of your questions. So I leave it to you. How do you map the states and actions while formulating MPTs? But yeah, sir has stated the MPTs. I hope you have gone through those. So this was your contextual bandwidth. I hope you don't have any doubts or concepts. Okay, so now for the full RL problem. So just a very quick introduction for the full RL problem. So you have an environment and you have an agent. The agent observes what state the environment is in. So environment might have different states. Agent will take different actions on the states. So it will observe at time instant t what the state of environment is, and then basing on that state that it sees what the environment is, it will take an action 80. So once it takes an action 80, the environment gives agent a reward rt plus 1 and also changes its state to st plus 1. So what you are seeing is what you see is st. The agent takes action 80. And yeah, so you get a reward 80 plus 1, and then you go to state st plus 1. So this continues. So now the agent takes 80 plus 1. The agent gets reward rt plus 2 and get to state st plus 2. Okay, so now could any of you say that this goes on where the randomness lies in this problem? There are two places where the randomness lies. Could any of you say where the two places the randomness lies?
So randomness while going from ST to ST plus 1.
Absolutely correct. Yeah, and one more.
The actions are random, right?
Yeah, so the action which you pick is random. Does anyone have a doubt on why the actions are random?
Yes, sir. I have a doubt there. Why action is random?
Okay, so since your state, so you agree that going from one state to another state is random, right?
Yes, sir.
So now suppose I take action A1. I might go to state S1, I might go to state S2, but with different probabilities, even if you take the same action each and every time.
Yes, sir.
Yeah, so A1 might have 0.5. So suppose there are two states, S1 and S2. Two actions, A1 and A2. Okay, so now if I take A1, S2 is a very bad state, S1 is a very good state. So if I go to S1, I'm like getting really high rewards. S2 is very bad. So if I take A1, which has 0.5 and A2 which has 0.3, what I'm trying to do is I'm trying to do a probabilistic sense of how, like, okay, sometimes I pick action 1 if I'm in state 1, sometimes I pick action 2. That thing comes from, I think, that thing comes from when you are in MAV also. So in MAV also, what you're trying to do is you're trying to maximize the probability that you're picking the action, but you don't know, so you want to explore also. So here what you do, by assigning a probability to the action from each state, you are trying to explore with less probability that what happens if I pick a bad action, but with more probability we will do the exploitation. Okay, I know that taking this action is very good. Do you understand why the randomness of the action?
Yeah. Okay. I'm getting. Yes,
Yes.
sir.
So
Aniket,
yeah.
sorry, I was thinking, I didn't know that eight, taking the same action will give us different states because I was thinking, I was imagining this in like a chessboard where,
Haha.
no,
Yeah. Yes. So uh,
always moving the pawn will
yeah.
always move the pawn from state one to state two, like that. I was thinking in that way.
Okay, but during in a chessboard, okay, so keep this very clear. If you move a pawn, that's fine, but that is not because environment also has to react to take you to st+1. So what is an environment in the chessboard in the chess game?
The configuration of the board itself, right? Where the pawn.
Opposition.
But the environment also includes some other person, your opponent. For the same action you take, your opponent could do different action and take the board to different states.
Okay, got it. Thank you.
Any more doubts? Yeah, I was hearing some other doubt. Hello.
It's fine, sir. I have no doubt. Yeah.
Okay, I think so. I think everything is fine with this. Okay, so okay, so you have states. So like mathematically defining, what you have is you have a state space. So S1, S2, as someone pointed out that configuration of chessboard is the chess, but configuration of chessboard after the environment reacts with you. The environment should give you the new state. Action you take is what you move the chess piece, but then your opponent would try to move something else. So after both of those actions, the state change. Now then you move, your opponent moves, new state. You move, your opponent moves, new state. And depending on your move and your opponent move, the opponent moves gives you how good your action was. That is your reward. Like if you have done a very good move, your opponent would be like very flustered and try to move a mode which takes you to better state, which has good reward. So it's in that sense. So you have an action states A1, A2, and so on. And now the probability traction matrix of S. Okay, I'll write it in. I might go off with Sir's notations. st+1 comma rt+1 given st comma et. Yeah. So yeah, previous state I take an action, I go to a new state. So this is one of the probability. I can split this into probability of st+1 given st comma at, this and expectation of rt+1 given st comma at comma st+1. I can split it into these two. So it's basically probability, but yeah, sometimes you don't know the whole distribution, so you get the first moment, which is fine. So I can split this into these two terms. I hope that also is clear to everyone. And then I have discounted factor gamma. Okay, I think I didn't cover the part where Sir told about returns before going to all this. But is the returns part clear to everyone? Do you have any doubt in the returns where Sir defined returns GT is equal to RT plus 1 plus 1 till RT, and why that capital T is random? So this is total return, and then GT is equal to RT plus 1 plus gamma RT plus 2 plus 1 if you have infinite. So there are multiple problem settings here. Something which has a end state. So that is called a finite terminating RL problem. If R that is deterministic, then it's very easy to solve. But if it's not, it's the finite state, you know what the finite state is, but you don't know at what time it will terminate. Then you have randomness in T. Some are infinite horizon problems. So where you don't have finite horizon, you have an infinite horizon problem. So it goes on. Problem goes on. So suppose something like inventory control. You have to do it daily. Like you have to do it infinite amount of time. You don't know what is a good time to stop. Like you have a company which does inventory control. you go on doing it, go on doing it, go on doing it. You don't, because you don't want the company to stop at any time. You just want to keep the company growing, growing, growing. So what happens? So actually, the discounted reward is what happens when you keep on adding till infinity is you get to a point where returns could be infinite. So that's why what you do is you bound it by gamma, by some gamma coefficient which is between 0 and 1. And what happens if gamma is greater than 1? So yeah, that is also a question that I'll let you think about. And then this is discounted return. Then there is expected return. So yeah, so if you have this setting, then the MDP would have a gamma. Even if you have this setting, the MDP would have a gamma, but the gamma is equal to 1. I hope that is also clear to you.
Can gamma be greater than 1?
Okay, you tell me what happens if gamma is greater than 1.
No, sir, I mean, I think, sir, if gamma into RT plus 2, then gamma square RT plus 3, and if that will be keep on increasing, then maybe, sir, this GT become unbounded.
Yeah. So what if I tell you that it has a terminal state?
Okay. In that case, it will not go unbounded.
Yeah. But then
Okay.
what will occur? Like, yeah, you think you're thinking in the right direction. So what will occur? So
So I think we are giving more importance to the rewards which are getting later stage
yeah,
than the immediate stage.
yeah,
Yes.
So that might be a problem.
yeah. So what would the algorithm give out? Like naturally, intuitively, what would the algorithm give out?
We want the policy to learn like for the immediate rewards, not the far rewards. So we
Yes,
will give preference to the nearby rewards.
you are right in one way, but like you're correct. You're correct. You're not wrong. You're not wrong. But like, what would happen if I put gamma greater than? You are right that I will try to do the long term rewards. That also you're correct. So,
Yeah.
uh, so what will any good algorithm try to do? Will it try to stop or will it try to go until infinity? Because it will see that I'm doing it for more time, I'm getting more reward. I'll do it for still more time, I'll get still more reward. So you get the point, right? Okay, I'll leave it up to thought, but you're right. You're right that it's looking at the later rewards.
Yeah.
Okay. So next there was an expected reward, which where GT was limit and tends to infinity. Okay, so RT plus 1 plus T plus 2 so on RT plus N. So this is also one of the returns that. So then for MDP to mathematically know an MDP, what are the things that you need to all the things that you need to know? You need to know the state space. So what you'll have is a mathematical formulation. You will have a crude game setting or a crude, very crude, what you say, a setting that will tell you, okay, this is I have a robot. If you take this action, it wants to go from here to here. It will take this action. If you take this action, it goes this. It does this. If it takes this action, it does this. There is a charging point. If it discharges, and all those things will be there. So what you need to boil down from that to make it into mathematical setting is first you need to know all the state spaces all the state spaces for that problem. So you have state space and action space, transition probability matrix S prime R given S comma A and gamma. Yeah, this thing can be broken into two, as I mentioned earlier. So this encapsulates your whole MD. So I hope there is no doubt in this part. And I think I've not even stated what value function is and whatnot. So if you have any doubt in the value function, you can ask what the value function is. Okay. So I hope you don't have any doubt. And okay, so I have done the Gaussian part in this. Okay. So what I'll do now is I'll quickly go through a code which I've stop. Share my screen. Is my screen visible?
Yes, sir.
Okay, it's visible now. Okay. So this is for the multi-arm magnets. So yeah, MDP, since just now only we have introduced all the MDPs and all, uh, we'll do the code part next. Like we'll come slowly with slowly, but this is for the multi-arm magnets. So yeah, so what you have is multi-arm magnet where you can pull each arm and you get reward for each. Right. So yeah, you know. Okay. So yeah, so now what I have is each arm, the underlying distribution previously, everything I'm taking it to be Gaussian. So now what I'm taking it different distributions for each and every arm. So it could be Gaussian with some mean and variance. It could be uniform between some this thing. It could be Poisson. It could be beta. It could be anything. But these are the true underlying distributions which you don't know for the arms. Okay, so then what you do is this function is that you pull an arm, it gives you reward from one of the distributions. Based on one of the distributions, it gives you a reward. So what we'll do is we'll just first try to pull 1,000 arms each time and see what mean I've got. So I've given the distribution. So this is the true mean and this is the estimated mean. So you can see that these are pretty close to each other. And yeah, so if you pull 1,000 times for each arm, you'll get. So the first two arms are Gaussian. The next two arms are, okay, first two arms are Gaussian, next two arms are uniform, next Poisson and next beta. I hope that is clear. And with different means. So the first is Gaussian with mean 0.37 and then 0.95. 0.37 Gaussian number is estimated to 0.4 and 0.9 Gaussian number is estimated to 0.5. So these are all rewards. So these are all the rewards. This probability is the probability of getting rewards from an arm which has an unknown distribution. I hope that is clear. So just let's plot the rewards. Okay, so see, so the arm 0. So first arm 0.
So your screen is not visible, I guess. For me,
Oh, is it a problem?
I don't know about.
No, I was able to.
Yeah, now it is visible. Yeah, now I can see.
Oh, okay.
Yeah, now it's fine. Thank you.
Okay, so do you want me to go from first or?
Yes, sir.
Okay. Anyhow, I'll put this code in the YouTube description so you could check the code anytime you want. So, okay, why am I doing it? Okay, so first you have, what I'm doing is I'm defining different distributions for each and every different arm. So I have two arms which are Gaussian, I have two arms which are uniform, I have two arms which are Poisson, I have two arms which are beta. And then I'm defining a function which says that if I pull an arm, I get a reward from the distribution. Okay, and then I'm pulling those arm 1,000 times, and then I'm calculating 1,000 times I get a sample reward from each and every arm from that distribution, which I don't know. So I just sample and I take the sample average. So since I know from where I'm sampling, I know the true mean, and since I've sampled 1,000 times, I'm calculating the estimated mean. So as you see that, yeah, they're close to each other, true mean and estimated mean. The first were Gaussian, next were uniform, next were Poisson, next were beta. And then I'm trying to plot like what reward I got in each and every time. So how many times I got the reward in each and every time. So this first were Gaussian. As you can see that, yeah, so I'm close to the mean. True mean and estimated mean. The next is uniform. You can see that, yeah, I'm pretty close. The next is Poisson. So you can see that exponential and decrease. So the Poisson distribution. I'm also close to the mean, Next is beta. Still I'm close to the both ends. Yeah. So I hope this is clear. Yeah. So now using this, I'll try to you guys actually will try to run epsilon grady or softmax or UCB. Yeah, UCB I think you need the support to be zero between 0 and 1. So you can run epsilon grady and softmax. So what you do is yeah, for epsilon grady you can write your code here. So how you pick an action, how do you increment this app, like for multi-arm mandates you need to keep a note on how many times you have picked an arm. So you need to write a code for incrementing the arm each time you have picked an arm, and then store it in that. And then you pull the arm to get a sample reward, and then store all the cumulative rewards, and then see which has the maximum reward, and then pick that. Yeah, so you can do whatever, like then you can run your code here, and then so yeah, then you can, what you do is you can plot your Q, the Q function that you have estimated there. So now since I have not run any code, it's all plain, it's all constant, but you guys can write your code here. The code is similar to the code that I showed last time for epsilon grady, and so you can do it for softmax because you know the algorithm for softmax, right? So you do the Q plotter, and yeah, this is, yeah, then this code. So you get some plots here. There's now no plots here. Okay, this, if you run the code, you'll get the code for epsilon. Now I have not done the code yet. So this is all open for you to do. So you can try for different epsilons what happens for different yeah, what happens if I have different epsilon values, what happens if I have different missing values. You can try out all those ones. So and you can see. And for anyone who was attending late, so last time when I showed a code, I think many of you were confused what I'm plotting because I had no proper denotions for this. So last time I was plotting the regret. I was not plotting reward. So I was not attaining maximum reward. I was trying to minimize the regret. So I hope that difference between plotting the maximum the difference between regret and reward is understood. So if you plot reward, what happens is the arm which goes high quickly is what you want to prefer. But in the last class I was plotting regret. So I don't want to go high quickly. I want my arm to decrease, like have less value. So the arm which was less had the better this. I hope that is clear. You guys have doubt in that? Regret and reward.
Regret is just how much time we are away from the optimal action, right?
So yeah, regret is at each time instant you get a reward, right? So reward minus what was the optimal arm that you could have done. So if you pick the optimal arm each and every time, regret would be 0 each and every time. That is what you want, optimal. So optimal regret is you want 0 each and every time, but you can't have regret 0 each and every time because you're exploring. So you'll have some regret positive and then you'll go at a constant time. So last time what I was saying was I was plotting the regret, but actually sir mentioned maximum reward. So sir was telling I want higher steep reward and then straight line, but the difference now plotting regret, I don't want high steep slope, I want low slope, I want really low slope, and I don't want it to go very high, I want it to cut it into a small thing. So the last time code which I shared in the discussion part, you will see there I plotted regret versus steps, not reward versus steps. But there will be problems where you try to minimize regret than maximize reward. So you need to be confident in both of those.
Yeah, thank you.
You guys have any more? Because today I'm doing it quickly because there is another session from 7 to 8. You guys also could attend it. It's taken by Manav. So I'm trying to do it quickly so that you guys can attend Manav also. Do you guys have any other doubt? Then ask me or if it's not, move on to next. Manav's investments. I will give some timers too for any questions.
Sir,
Yeah, yeah,
sir, in real life, when the number of states are infinity, and for example, because from the control system background I am having,
yeah, yeah.
uh, so in a continuous setting, the number of states are infinity. So in that case, how to actually handle those things?
Yeah.
And action is also control input to a system.
Yes,
So there
yes,
are many control inputs. So in that
yes,
case, please
yes.
could you let me know?
Yeah, so there are multiple ways to handle. Okay, so one by one I'll do. So your continuous state space, continuous action space. First, I'll do continuous action space. Since you're from control background, so maybe you're thinking like something. Maybe I have an actuator. I could go from 0 to 1. So I could take any number between 0 to 1 to actuate something.
Yes.
Now 0 to 1, you have uncountable number of action space, right? Because it could be 0.005, 0.0009, it could be uncountable number between 0 and 1. So what you do is you discretize the action space. So you say that the more you discretize with small t, you higher dimension, but you discretize the action space. You understand that you can discretize the action space.
Yes, yes.
So if your action space is infinity, I suggest there is one method of discretizing it and doing it. But yeah, so action space is discretizing. Now continuous state space, that is a bit tricky. Continuous state space, I think sir will come answer those doubts while sir is, I think in some of where there are, I'm not sure where sir will go into it, but yeah, as weeks go on, you'll see where the continuous state space but I think that is an active topic of research and still much research is not been done in continuous state space. But there are papers on continuous state space. You can look up. But I'm not sure how continuous state space can be handled. But I hope your doubt of continuous action space is clear.
Yes, sir. Yes, sir. That is clear. Yes, sir.
Yeah. Any more? Yes. Any more?
Sir, as the sir spoke in the lecture, if we try to update the optimal action using neural networks,
Oh yes, yes,
then
yes.
how we update the weights, sir? Like if we backtrack the loss or rewards, sir. Like
Oh, that
uh,
that is yeah. That's a good question. You can backtrack loss and you can backtrack rewards. If you're so when you have a neural network setting, you can minimize some function, you can maximize some function. But I think most of the setting is
okay,
minimizing a function, right? When you are doing a neural network.
yeah, yes, sir. In neural
So
network, we minimize the loss.
yeah, you minimize the loss. So you can convert. That is what I was saying. You can convert your reward to a regret setting, and then you could do it.
Okay,
But then, since you don't know
yeah,
what your optimal time part is, so backtracking would be difficult in the minimize setting. So you maximize expected reward, but then what you do is minimize minus of expected reward. I hope that is clear.
okay, yeah, I get that.
Yeah. So
Yeah, thank you.
yeah, yeah. Any more? I have 2 minutes left. I'll be here for 2 minutes. Then you guys can join.
Aniket, where have you shared the links to the notebooks?
Okay, so in the NPTEL web page,
Mhm.
down there is a this thing called live sessions.
Yeah,
They'll
problem solving sessions,
problem
yes.
solving. They'll find an Excel sheet.
Correct.
In that, the second there is a link for YouTube and there is another link for my Google Drive.
Yeah, the Google Drive just has PDFs, it looks like.
Yeah, so I am uploading these PDFs. What else do you want? Like,
The Colab notebook.
oh, the collab notebook from today onwards. This collab notebook I'll be putting on YouTube description.
Okay, this and even last week also you had one, right?
Last week I put it in the okay, I put it in the forum discussion, Google forum
Oh,
discussion.
okay, okay, I'll get it. Thank you.
So someone has asked me for that.
Hmm.
That was very crude form of code. So yeah, I have not written.
Okay,
If you guys could update that and do some good things with that and share it back to me, it would be nice.
sure.
Yeah.
Yeah.
Okay. Uh, yeah. So I think it's 7. I'll close this meeting because yeah. So there are a lot of people joining. So
Thanks for the session, sir.
no worries.
Thank you, sir.
See you.
Thank you, sir.